From the smallest atom to the largest galaxy, every single thing in existence is turning. Right now, as you lie here perfectly still, you're actually spinning through space at over 1,000 miles per hour. The Earth beneath you rotates, the planet orbits the sun circles the center of our galaxy, and the galaxy itself spins through the vast darkness of space. Everything, absolutely everything, is in constant motion. And yet, here you are, feeling completely motionless, suspended in the calm of this moment. Tonight, we'll drift into the quiet rhythm of motion that has shaped everything since the dawn of time. We'll explore the gentle dance that connects the tiniest particles in your body to the massive spirals of galaxies billions of light years away. Where did the first motion come from after the Big Bang? And how does that initial twist keep everything spinning, even the fabric of space itself? To understand why everything spins, we need to start with a simple but powerful idea. It's called angular momentum. Now, don't let the technical name worry you. Think of it this way. Angular momentum is just a measure of how much an object wants to keep spinning once it starts. It's the universe's way of remembering motion. Once something starts turning, it wants to keep turning. This isn't magic. It's one of the most fundamental laws of physics, and it explains almost everything about the motion we see in the cosmos. Imagine a figure skater on the ice. When they start spinning with their arms stretched out wide, they turn slowly and gracefully. Their body moves through the air, tracing circles. But then watch what happens. The skater pulls their arms in close to their body. Suddenly, something amazing occurs. They spin faster and faster. Their rotation accelerates dramatically. They become a blur of motion. The skater didn't add any new energy. They didn't push off the ice again. They didn't use their muscles to spin harder. They simply changed their shape. They brought their mass closer to their center, and that change made them spin faster. This is the law of conservation of angular momentum at work. The law states that in a closed system, the total angular momentum stays the same. It can't be created or destroyed. It can only be transferred from one object to another or redistributed within the same object. When the skater pulls their arms in, they're making themselves more compact. They're reducing what physicists call their moment of inertia. That's just a fancy term for how spread out their mass is. To conserve angular momentum, when the moment of inertia decreases, the rotation speed must increase. It's a trade. Less spread equals more speed. This trade happens automatically. The universe enforces it through the laws of physics. You can't cheat it, you can't break it. It's as reliable as gravity. This same principle applies everywhere in the universe. It applies to ice skaters, it applies to spinning tops, it applies to hurricanes, it applies to collapsing clouds of gas in space. It applies to everything that rotates, and once you understand this law, you start seeing it everywhere. You start recognizing its signature in the motion of planets, stars, and galaxies. The conservation of angular momentum is the invisible hand that shapes the rotating cosmos. It's the reason why planets orbit stars. It's the reason why galaxies have spiral arms. It's the reason why your washing machine needs to be balanced. Everything connects back to this one elegant principle. But here's the question that should be nagging at you. Where did the first spin come from? If angular momentum is conserved, if it can't be created or destroyed, then how did the universe get its spin in the first place? To answer that, we need to travel back to the very beginning, back to the moment of creation, back to the Big Bang. About 13.8 billion years ago, the universe burst into existence from a single point, a point smaller than an atom, smaller than a proton, perhaps infinitely small. We call this point a singularity. At that moment, all the matter and energy that would ever exist was compressed into this tiny space. The temperature was unimaginably hot. The density was infinite. And then, in a fraction of a second, so small that it's hard to even comprehend, space itself exploded outward. This wasn't an explosion in space. It was an explosion of space. Space itself expanded. It grew faster than the speed of light. This period is called inflation. In less than a trillionth of a trillionth of a trillionth of a second, the universe expanded from smaller than an atom to roughly the size of a grapefruit. And it kept expanding. Even today, 13.8 billion years later, the universe is still expanding. Galaxies are moving away from each other, space itself is stretching, the expansion continues. But in those first moments, in that initial burst, the universe took on its basic character: energy transformed into matter. The fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, all separated from each other. They had been unified at the extreme temperatures of the singularity, but as the universe cooled, they became distinct, and the universe was almost perfectly smooth. Almost. The early universe was incredibly uniform. If you could have taken a photograph of it a few 100,000 years after the Big Bang, it would have looked almost the same everywhere. A hot, glowing soup of particles and radiation. But not quite the same. There were tiny variations, little ripples in the density. Some regions had slightly more matter than others. These differences were incredibly small, only about 1 part in 100,000. That means that if one region had 100,000 particles, another region might have 100,001. That's how small the variations were, but they were there, and they were crucial. These tiny asymmetries, these little ripples, were the seeds of everything that would come later. They were the seeds of galaxies, stars, planets, and ultimately, life. But where did these ripples come from? This is one of the deep mysteries of cosmology. The leading theory is that they arose from quantum fluctuations. At the quantum level, the level of atoms and particles, nothing is ever truly still or smooth. There's always uncertainty, always randomness, always fluctuation. During inflation, when the universe was expanding so rapidly, these tiny quantum fluctuations were stretched out to enormous sizes. They were amplified. They were frozen into the fabric of space, and they became the density, variations we observe. These variations weren't just differences in density. They also included differences in motion. Some regions had a slight tendency to move in one direction, others moved in a different direction. There was turbulence, there was jitter, there was motion, and crucially, there was rotation. Not every region rotated in the same direction, it was random. But each region had some small amount of angular momentum. Some had a little bit of clockwise rotation, some had counterclockwise, some had rotation around one axis, some around another. It was chaotic. But the key point is that angular momentum existed. It was built into the structure of the early universe through these quantum fluctuations. As the universe expanded and cooled, gravity began to take over. The regions with slightly higher density had slightly stronger gravity. They pulled matter toward them. They grew. They became more dense. And as they grew, they pulled in matter from the surrounding regions. This matter brought its own angular momentum with it. Some of this angular momentum canceled out. If matter spinning clockwise merged with matter spinning counterclockwise, the net result might be no rotation. But statistically, there was always some leftover, some net angular momentum that didn't cancel. And that net angular momentum was preserved. It was carried forward as the structure continued to grow. This is where the conservation of angular momentum becomes so important. Once a region of space has some net rotation, even a tiny amount, that rotation is locked in. It can't disappear. As the region collapses under its own gravity, becoming more compact, the rotation must speed up. Just like the ice skater, the cloud of gas shrinks, its moment of inertia decreases, and to conserve angular momentum, its rotation speed increases. This is inevitable. It's required by the laws of physics. You can't have gravitational collapse without this happening. The rotation accelerates, the cloud spins faster and faster, but there's a limit. There's only so fast something can spin before it starts to tear itself apart. Imagine spinning a ball on a string. If you spin it fast enough, the string breaks. The ball flies off. The same thing happens with rotating clouds of gas in space. As the cloud spins faster, the material at the outer edges experiences centrifugal effects. It feels a force pushing it outward. This isn't a real force in the technical sense. It's an apparent force that arises because we're observing from a rotating reference frame. But the effect is real. The material wants to fly outward. And at some point, if the rotation gets fast enough, the outward push becomes stronger than the inward pull of gravity. The cloud can't collapse any further in that direction. It stops shrinking radially. But it can still shrink in other directions. Specifically, it can still shrink perpendicular to the rotation axis. So what happens? The cloud flattens. It spreads out into a disk, a spinning disk. This disk lies in a plane perpendicular to the rotation axis. the cloud collapses in the direction parallel to the rotation axis, becoming thinner. But it maintains its size or even expands slightly in the plane of rotation. The result is a flattened, spinning structure. This process is called the formation of an accretion disk. And it happens everywhere in the universe where rotating material collapses. It happens when stars form, it happens when planets form, it happens when galaxies form. It's a universal process. Rotation plus gravity equals a disk. This is one of the most common structures in astronomy. Disks are everywhere. The rings of Saturn are a disk. The asteroid belt is a flattened disk. The solar system itself is a disk. The Milky Way galaxy is a disk. Accretion disks around black holes are disks. They all form through the same basic mechanism. In the center of a collapsing cloud, where most of the mass concentrates, conditions become extreme. The density increases, the temperature rises, atoms collide with each other more and more frequently. The pressure builds. And eventually, if the cloud is massive enough, the temperature at the center gets so high that nuclear fusion begins. Hydrogen atoms, the simplest and most common element in the universe, are squeezed together so hard that they fuse into helium. This process releases enormous amounts of energy. The energy pushes outward, creating pressure that balances the inward pull of gravity. The collapse stops. The cloud has become a star, a stable, shining sphere of hot gas, powered by nuclear fusion at its core, and this star rotates. It inherited the angular momentum of the cloud that formed it. It spins as it shines. Around the new star, in the flatter parts of the disk, the remaining gas and dust continue to orbit. Over time, particles in this disk collide with each other. Sometimes they stick together. Grain by grain, dust mote by dust mote, they build up larger objects. These objects, called planetesimals, are the building blocks of planets. They can be a few kilometers across. They have enough gravity to attract other nearby material. They grow. They sweep up more and more of the disk. Some planetesimals collide and merge, forming even larger bodies. This process continues over millions of years. Eventually, the largest of these bodies become planets. They've gathered most of the material in their orbital zone. They orbit the star in nearly circular paths, and they rotate on their own axes, spinning as they orbit. This is how our solar system formed. About 4.5 billion years ago, a giant cloud of gas and dust, part of a larger molecular cloud in our galaxy, began to collapse. Perhaps it was triggered by a nearby supernova, the explosion of a massive star that sent a shockwave through the cloud. The cloud began to contract under its own gravity. It had some net rotation inherited from the motions within the molecular cloud. As it collapsed, it spun faster. It flattened into a disk. At the center, the density and temperature became high enough for nuclear fusion to ignite. Our sun was born. It was a young, active star, more energetic than it is today, with powerful stellar winds and frequent flares. In the disk around the young sun, dust grains began to stick together. Close to the sun, where the temperature was high, only materials with high melting points could condense into solid form. Metals and rocky materials survived. This is why the inner planets, Mercury, Venus, Earth, and Mars, are rocky. They're made of iron, silicon, oxygen, and other elements that remain solid despite the heat. Farther from the sun, beyond what's called the frost line, the temperature was low enough for water ice and other volatile compounds to condense. This is where the giant planets Jupiter, Saturn, Uranus, and Neptune formed. They started with rocky cores, but they also gathered huge amounts of ice and gas. They became massive balls of hydrogen, helium, and various ices. Jupiter alone contains more mass than all the other planets combined. It's so large that it almost became a star itself. If it had been about 80 times more massive, its core would have reached the temperatures needed for fusion. But it didn't quite make it. Jupiter remains a planet, though it still radiates more heat than it receives from the sun, a remnant of the energy from its formation and ongoing gravitational contraction. Each planet in our solar system carries the story of its formation. In its rotation, they all rotate. They all orbit in the same direction, counterclockwise, when viewed from above the sun's north pole. This is because they all formed from the same rotating disk. The disk's rotation determined the direction of planetary orbits and their spins. But there are variations. Some planets rotate faster than others. Some have different tilts to their rotation axes. These differences tell us about the collisions and interactions that occurred during the chaotic early days of the solar system. Our Earth spins on its axis once every 24 hours. That rotation gives us day and night, one of the most fundamental rhythms of life on our planet. But why does Earth spin at all? Why 24 hours? Why not faster or slower? The answer lies in those early days of the solar system. Earth formed from countless collisions between smaller objects. Each object that crashed into the growing Earth brought its own momentum with it. Some hit from one direction, some from another. Most of this was random. But there was a statistical tendency. The overall motion of material in Earth's part of the disk was in one direction. So even though individual collisions were random, they didn't all cancel out. There was a net angular momentum. The collisions added up, they gave Earth its spin. In fact, one of the most important events in Earth's early history was a massive collision that may have created our moon. About 50 million years after the solar system formed, a Mars-sized object, which scientists have nicknamed Theia, crashed into the young Earth. The impact was catastrophic. It vaporized huge amounts of rock. It melted much of Earth's surface. Debris from both Earth and Theia was thrown into orbit around our planet. This debris formed a disk which quickly coalesced into the moon. This giant impact had several important consequences. It increased Earth's rotation rate. Before the impact, Earth may have been spinning more slowly. The collision added angular momentum. It also tilted Earth's rotation axis, giving us the seasons. And it gave us our large moon, which has had profound effects on Earth's evolution, stabilizing our axial tilt, creating tides, and possibly even playing a role in the development of life. But Earth's rotation isn't constant. It's gradually slowing down. This has been happening for billions of years, and it will continue into the future. The culprit is our moon. The gravitational interaction between Earth and the moon creates tidal forces. You're probably familiar with the ocean tides, the rising and falling of sea level that happens twice a day. These tides are caused by the moon's gravity. The moon pulls on the Earth, and because gravity gets weaker with distance, the moon pulls slightly harder on the side of Earth facing it than on Earth's center, and harder on Earth's center than on the far side. This difference in gravitational pull creates a stretching effect. On Earth, which is not a rigid body, this stretching causes the oceans to bulge. There's a bulge on the side facing the moon, and another bulge on the opposite side. Now, here's the key point. Earth rotates faster than the moon orbits. Earth spins once every 24 hours, but the moon takes about 27 days to orbit Earth, so the tidal bulges don't stay lined up with the moon. Earth's rotation drags the bulges ahead of the moon. The bulge on the near side of Earth is slightly ahead of the line connecting Earth and the moon. This means the bulge has a gravitational pull on the moon. It pulls the moon forward in its orbit, speeding it up. By Newton's third law, the moon pulls back on the bulge, slowing Earth's rotation. This is tidal friction. The moving tides, especially the ocean tides, create friction against the ocean floor and coastlines. This friction dissipates energy as heat, and that energy comes from Earth's rotational energy. As Earth loses rotational energy, it spins more slowly. The effect is small. Earth's rotation is slowing by about 1.7 milliseconds per century. That means a day-to-day is about 1.7 milliseconds longer than a day was 100 years ago. You wouldn't notice this in your lifetime. But over geological timescales, it adds up. We can actually see evidence of this in the fossil record. Certain corals and other organisms lay down daily growth rings, like tree rings. By counting these rings in ancient fossils, paleontologists have determined that days were shorter in the past. About 350 million years ago, in the Devonian period, a year had about 400 days. Each day was shorter, only about 22 hours long. Going back even further to the time when the moon first formed, days on Earth may have been only 5 or 6 hours long. The moon was much closer to Earth back then, and its tidal forces were much stronger, but Earth was also spinning much faster. Over billions of years, tidal friction has lengthened our days and will continue to do so. As Earth's rotation slows, what happens to that lost angular momentum? It doesn't disappear. Remember, angular momentum is conserved. It can't be destroyed. Instead, it's transferred to the moon's orbit. The moon's orbital angular momentum increases. And when an object's orbital angular momentum increases, something interesting happens. The orbit gets larger, the object moves farther away. So as Earth slows down, the moon is gradually moving away from us. Every year, the moon drifts about 3.8 centimeters farther from Earth. That's roughly the rate your fingernails grow. We can actually measure this drift using laser ranging. Astronauts on the Apollo missions left reflectors on the moon's surface. Scientists on Earth shoot laser beams at these reflectors and time how long it takes for the light to bounce back. By measuring this time very precisely, we can determine the exact distance to the moon. And by repeating these measurements over many years, we can see that the moon is indeed receding. This process will continue into the far future. Eventually, billions of years from now, Earth's rotation will slow down so much that one side of Earth will always face the moon. At that point, the day will be much longer than it is now, perhaps equal to about 50 of our current days. Earth will be tidally locked to the moon, just as the moon is already tidally locked to Earth. When that happens, the moon will hang motionless in the sky over one hemisphere of Earth, never rising or setting. People on the other hemisphere would never see the moon at all. The moon will be much farther away than it is now, perhaps 50% farther. It will appear smaller in the sky. Total solar eclipses, which are currently a spectacular sight because the moon and sun appear almost exactly the same size, will no longer be possible. The moon will be too small to fully cover the sun. Of course, this future scenario assumes nothing else interferes. In reality, the sun will become a red giant in about 5 billion years, long before Earth and moon become mutually tidally locked. The sun will swell up, perhaps engulfing Mercury and Venus, and possibly reaching Earth's orbit. Life on Earth will end long before that, as the sun gradually brightens over the coming billion years, eventually making our planet too hot for liquid water to exist on the surface. But the tidal interaction between Earth and moon will continue as long as both bodies exist. It's a slow, patient process, playing out over geological ages, driven by the fundamental laws of gravity and angular momentum conservation. The moon itself shows us what tidal locking looks like. The same side of the moon always faces Earth. From our perspective, the moon doesn't appear to rotate at all, but it does rotate. It rotates once every 27.3 days, which is the same as its orbital period around Earth. This synchronization is not a coincidence. It's the result of tidal locking. Early in the moon's history, it likely rotated faster. But Earth's gravity created tidal bulges on the moon. Just as the moon creates tides on Earth, Earth creates tides on the moon. These lunar tides are much stronger than Earth's ocean. Tides because Earth is much more massive than the moon and exerts a much stronger gravitational pull. The tidal bulges on the moon created friction and dissipated energy. Over millions of years, this friction slowed the moon's rotation until it matched its orbital period. At that point, the bulges stopped moving relative to the moon's surface. The friction stopped. The moon became locked, one face forever turned toward Earth. We call the side facing Earth the near side and the side facing away the far side. The far side is sometimes incorrectly called the dark side, but it's not dark. It receives just as much sunlight as the near side. We just never see it from Earth. The far side and near side of the moon are surprisingly different. The near side has large, dark, flat regions called maria, which are ancient lava plains. The far side has very few maria and is heavily cratered. This asymmetry is still not fully understood, but it may be related to the moon's formation and the fact that Earth's gravity affected how the moon's crust formed and solidified. Tidal locking is common throughout the solar system. Most of the large moons of the giant planets are tidally locked to their parent planets. Jupiter's 4 largest moons, Io, Europa, Ganymede, and Callisto, are all tidally locked. Saturn's large moons, including Titan, are tidally locked. Even Pluto and its largest moon Charon are mutually tidally locked to each other, an unusual situation where both bodies always show the same face to each other. They're locked in a permanent stare, orbiting their common center of mass. Now let's zoom out. Let's leave the Earth. And moon behind. Let's leave the solar system. Let's think about something much larger, an entire galaxy. Our home galaxy, the Milky Way, is a vast island of stars in the cosmos. It contains about 200 billion stars, maybe more. Recent observations suggest the number could be as high as 400 billion. Each of these stars is a sun, many with their own planetary systems. The Milky Way also contains vast clouds of gas and dust, regions where new stars are being born. It contains remnants of dead stars, white dwarfs, and neutron stars, and black holes. And binding it all together, providing the gravitational glue that keeps the galaxy from flying apart, is dark matter, a mysterious substance we'll talk more about in a moment. The Milky Way is shaped like a disk with a central bulge. If you could view it from the side, it would look like two fried eggs placed back to back. The disk is where most of the stars are, arranged in spiral arms that wind outward from the center. Our sun is located in one of these spiral arms, about 2/3 of the way out from the galactic center in a relatively quiet neighborhood. The central bulge is a densely packed region of old stars, and at the very center of the galaxy, hidden behind clouds of gas and dust, lies a supermassive black hole. We've named it Sagittarius, a star, because it's located in the direction of the constellation Sagittarius. The Milky Way rotates. The entire galaxy spins like a gigantic cosmic whirlpool. But it doesn't rotate like a solid object. If you've ever watched a wheel or a record player spin, you've seen solid body rotation. Every part of the wheel takes the same amount of time to complete one rotation. The outer edge moves faster in terms of speed, covering more distance per unit time, but the rotation period is the same everywhere. Galaxies don't work like that. They exhibit what's called differential rotation. Different parts of the galaxy take different amounts of time to complete an orbit around the galactic center. Our sun, for example, takes about 230 million years to orbit the galactic center once. We call this a galactic year. In the entire history of Earth, about 4.5 billion years, the sun has completed only about 20 orbits, 20 galactic years. The last time the sun was in its current position in the galaxy, dinosaurs had just begun to diversify on Earth. The time before that, complex multicellular life was just emerging in the oceans. Stars closer to the galactic center orbit faster. They complete an orbit in less time than the sun does. Stars farther out take longer. This differential rotation is a natural consequence of how gravity works. The farther you are from the center of mass, the weaker the gravitational pull, and the slower your orbital speed needs to be to maintain a stable orbit. But here's where things get strange. When astronomers measured the orbital speeds of stars at different distances from the galactic center, they found something unexpected. According to Newton's laws of gravity, stars at the outer edges of galaxies should be orbiting slowly, very slowly. As you move farther from the center, there's less mass inside your orbit, pulling you inward, so you should move slower. But that's not what we observe. Stars at the outer edges of the Milky Way and of other galaxies are moving much faster than they should be. In fact, they're moving almost as fast as stars closer to the center. This doesn't make sense based on the visible matter we can see. If you add up all the stars, all the gas, all the dust, everything we can observe in a galaxy, there isn't enough mass to explain the fast rotation speeds at the outer edges. The gravity from visible matter alone isn't strong enough to keep those fast-moving stars in orbit. They should be flung out into intergalactic space, like water flying off a spinning wheel, but they're not. The galaxies hold together. Something else must be providing the extra gravity needed to keep the stars in their orbits. That something is dark matter. Dark matter is one of the greatest mysteries in modern science. We can't see it. It doesn't emit light, it doesn't absorb light, it doesn't reflect light. It's completely invisible to all our telescopes and instruments. But we know it's there because of its gravitational effects. Dark matter has mass, and mass creates gravity. By observing how galaxies rotate, how galaxies move within clusters of galaxies, and how light from distant objects is bent by intervening mass, astronomers have determined that dark matter makes up about 85% of all the matter in the universe. Everything we can see, every star, every planet, every galaxy, all the gas and dust, makes up only about 15%. The rest is this mysterious dark substance. What is dark matter? We don't know. It's not made of atoms, at least not ordinary atoms like the ones that make up you and me. If it were, we'd be able to detect it through its interactions with light. Dark matter seems to interact with ordinary matter only through gravity. It doesn't feel the electromagnetic force. It doesn't participate in the strong nuclear force. It might interact through the weak nuclear force, but even that is uncertain. Scientists have proposed many candidates for what dark matter might be. One leading idea is that dark matter consists of hypothetical particles called WIMPs, weakly interacting massive particles. These would be particles that have mass, but don't interact with light or ordinary matter except through gravity and possibly through weak nuclear interactions. Experiments deep underground and in space are searching for WIMPs, trying to detect the rare occasions when a WIMP might collide with an ordinary atom. So far, no definitive detection has been made. Another possibility is that dark matter is made of axions, very light particles that were predicted to solve a problem in particle physics. Or perhaps dark matter is made of primordial black holes that formed in the early universe rather than from collapsing stars. Or maybe it's something else entirely, something we haven't thought of yet. The search for dark matter is one of the most active areas of research in physics and astronomy. Understanding what it is would be a major breakthrough, revealing a whole new component of the universe that has been hidden from us. For now, we can map where dark matter is by observing its gravitational effects. Dark matter forms a halo around galaxies. It extends well beyond the visible edges of galaxies, creating a large, roughly spherical cloud of invisible mass. This dark matter halo provides the extra gravity needed to explain the rotation curves, the relationship between distance from the galactic center and orbital speed. The flat rotation curves we observe, where stars far from the center move almost as fast as stars near the center, are a clear signature of dark matter. Without it, galaxies as we know them couldn't exist. They would either fly apart or have very different structures. At the heart of most galaxies, including our own, lies an even more mysterious object, a supermassive black hole. Black holes are regions of space-time where gravity is so strong that nothing can escape, not even light. They form when a massive amount of matter is compressed into a tiny volume. The boundary around a black hole, beyond which nothing can escape, is called the event horizon. Once something crosses the event horizon, it's gone forever. From our perspective, at least, it can never send us information. It's lost to the outside universe. Stellar mass black holes form when massive stars explode as supernovas and their cores collapse. These black holes can be a few times to a few tens of times the mass of the Sun. But supermassive black holes are in a different category entirely. They have masses millions or even billions of times the mass of the Sun. Our galaxy's central black hole, Sagittarius A star, has a mass of about 4 million suns. It sounds huge, but it's actually on the smaller side for a supermassive black hole. Some galaxies have black holes with masses of billions of solar masses. We don't fully understand how supermassive black holes formed. They were probably present early in the universe's history. They may have formed from the direct collapse of massive gas clouds, or from the mergers of many smaller black holes, or from the remnants of the first generation of stars. Whatever their origin, they've grown over billions of years by accreting gas and by merging with other black holes when galaxies collide. And they rotate. Black holes can have angular momentum, just like any other object. In fact, rotating black holes are probably the norm. When matter falls into a black hole, it brings its angular momentum with it. This causes the black hole to spin. A rotating black hole is described by Einstein's general theory of relativity. The solution to Einstein's equations for a rotating black hole was found by a physicist named Roy Kerr in 1963. We call it a Kerr black hole. A Kerr black hole has some fascinating properties. It has two event horizons, an outer and an inner one. Between them is a region called the ergosphere. In the ergosphere, space-time itself is dragged around by the black hole's rotation. Nothing in the ergosphere can stay still. Everything must rotate in the same direction as the black hole, swept along by the current of space-time. This effect is called frame dragging. Frame dragging is one of the strangest predictions of general relativity. To understand it, we need to think about what space-time really is. In everyday language, we think of space and time as separate things. Space is the stage on which events happen. Time is the progression of those events. But Einstein showed that space and time are intimately connected. They're part of a single, unified entity called space-time. Space-time is a four-dimensional fabric, 3 dimensions of space and 1 of time. And this fabric is not rigid, it's flexible. It can bend, it can curve, it can even twist. Massive objects create curves in space-time. We experience these curves as gravity. The Earth orbits the Sun not because there's a force pulling it, But because the sun's mass curves space-time, and the Earth follows the straightest possible path through that curved space-time, that path happens to be an ellipse. This is a beautiful and profound insight. Gravity is not a force, it's geometry, it's the shape of space-time. But Einstein's equations also predict that rotating objects do something additional. They don't just curve space-time, they twist it, they drag it along with their rotation. Imagine space-time as a thick fluid, like honey. If you place a heavy ball in the honey, it creates a dip. That's the curvature caused by mass. Now imagine the ball is spinning. As it spins, it grabs the honey around it and drags it along. The honey near the ball starts rotating with it. This is frame dragging. Space itself, right next to a rotating object, is dragged into rotation. For ordinary objects, even massive ones like planets and stars, the frame dragging effect is incredibly tiny. For Earth, the effect is so small that it took decades of effort and an extraordinarily precise space mission to measure it. That mission was Gravity Probe B, which we mentioned earlier. Launched in 2004, it carried 4 gyroscopes, the most perfectly spherical objects ever made by humans. These gyroscopes were pointed at a distant star. If space-time were not being dragged by Earth's rotation, the gyroscopes should have stayed pointed at that star indefinitely, to within the limits of measurement precision. But Einstein's theory predicted that Earth's rotation would drag space-time, and this dragging would cause the axes of the gyroscopes to drift slowly over time. The mission lasted over a year, collecting data. The analysis was painstaking because the effect was so small and there were many other effects to account for. But in the end, the results were clear. The gyroscopes had drifted, and the amount of drift matched Einstein's prediction. Frame dragging is real. Earth drags space-time around with it as it rotates, creating a tiny twist in the fabric of the universe. It's an incredibly subtle effect at Earth scale, but it's measurable. And it's a direct confirmation of one of the strangest predictions of general relativity. For black holes, especially rapidly rotating ones, frame dragging becomes much more dramatic. The closer you get to a spinning black hole, the more space-time is dragged. In the ergosphere, the dragging is so strong that nothing can resist it. Even a beam of light trying to remain still would be swept around. If you fell into the ergosphere, you would find yourself being carried around the black hole, faster and faster, unable to stop or even slow down. You would orbit the black hole at speeds approaching the speed of light, caught in the maelstrom of twisted space-time. Some black holes spin incredibly fast. The fastest rotating black holes we've observed are spinning at close to the maximum rate allowed by physics. At the maximum, the event horizon would be moving at the speed of light. That's the theoretical limit. You can't spin faster than that because nothing can exceed the speed of light. These ultra-fast spinning black holes are nature's most extreme gyroscopes, storing enormous amounts of angular momentum in the warped fabric of space-time. The frame dragging around these black holes has practical implications, at least in theory. A physicist named Roger Penrose realized that you could extract energy from a rotating black hole using frame dragging. The idea is called the Penrose process. You drop an object into the ergosphere. The object splits into 2 pieces. One piece falls into the black hole, the other piece escapes. If you do this correctly, the escaping piece can carry more energy than the original object had. Where does the extra energy come from? It comes from the black hole's rotational energy. You've slowed the black hole down very slightly and extracted some of its spin energy. This process could, in principle, be used by a very advanced civilization to power itself. A rotating black hole could serve as an enormous battery, storing energy that could be tapped over time. Now let's shift our perspective dramatically. We've been talking about the largest scales, galaxies, and black holes. Let's go to the opposite extreme. Let's talk about the smallest scales, atoms and particles. Do atoms spin? The answer is yes, but in a way that's much stranger than anything we've discussed so far. In the quantum world, the world of the very small, particles have a property called spin. Electrons have spin, protons have spin, neutrons have spin, even photons, particles of light, have spin. But here's the crucial and confusing point. Quantum spin is not the same as the classical spinning we've been talking about. An electron is not a tiny ball rotating on its axis. In fact, as far as we know, electrons have no size at all. They're point particles. How can a point spin? It can't. Quantum spin is something different. It's an intrinsic property of particles, like mass or electric charge. Every electron has the same amount of spin, always. You can't speed it up or slow it down. You can't stop it. The spin is just part of what an electron is. So why do we call it spin? The reason is historical and mathematical. When physicists first discovered this property of electrons in experiments, they didn't know what it was, but it behaved mathematically like angular momentum. It added to the total angular momentum of a system. It could be transferred between particles. It affected how particles interacted with magnetic fields, just like a spinning charged object would. So they called it spin, even though they knew it wasn't really spinning in the classical sense. The name stuck. Now we're stuck with it, and it causes endless confusion. Think of quantum spin more like a label. Electrons can be spin up or spin down. These aren't directions in physical space. They're quantum states, two possible configurations. You can choose any axis you like, and the electron can be in a state of spin up along that axis or spin down along that axis. But once you measure it, you'll always find it in one of those two states, never in between. This is one of the strange features of quantum mechanics. Certain properties, like spin, are quantized. They come in discrete values, not continuous ranges. Despite being weird and non-intuitive, quantum spin has enormous consequences for the world we live in. It's responsible for much of chemistry and material science. Here's why. There's a rule in quantum mechanics called the Pauli exclusion principle, named after physicist Wolfgang Pauli. It states that no two fermions can be in the same quantum state. Fermions are particles with half-integer spin, like electrons, protons, and neutrons. The exclusion principle means that if you have two electrons in an atom, they can't both be in exactly the same state. They have to differ in some way. One way they can differ is in their spin. An electron can be spin up or spin down. So in any given energy level in an atom, you can fit two electrons, one spin up and one spin down. If you try to add a third electron, it has to go into a different energy level, a higher one. This is why atoms have their shell structure. The innermost shell can hold 2 electrons, the next shell can hold 8. The pattern continues, and this structure determines how atoms bond with each other, which elements are reactive, which are inert, and how molecules form. Without quantum spin and the Pauli exclusion principle, all electrons in an atom would fall down to the lowest energy state. Atoms would collapse. They would be tiny, dense objects. Chemistry as we know it wouldn't exist. Molecules wouldn't form. There would be no water, no proteins, no DNA. Life would be impossible. So even though quantum spin isn't really spinning, even though it's a purely quantum property with no classical analog, it's absolutely essential to the existence of matter as we know it. Quantum spin also gives rise to magnetism. A spinning, charged object creates a magnetic field. An electron has charge and it has spin, so it creates a tiny magnetic field. In most materials, the spins of electrons are oriented randomly and their magnetic fields cancel out. But in some materials, called ferromagnets, the spins can align. All the little magnetic fields point in the same direction, adding up to a large macroscopic magnetic field. That's what a magnet is, a material where electron spins are aligned. When you pick up a paperclip with a magnet, you're witnessing a quantum effect. The aligned spins of billions of electrons in the magnet are creating a force strong enough to lift the paperclip against Earth's gravity. Quantum spin plays a role in technology too. The hard drive in your computer stores information using magnetism. Each bit of data, each 0 or 1, is represented by the magnetic orientation of a tiny region of material. That magnetism comes from aligned electron spins. The phenomenon of spin is also the basis of a field called spintronics, which aims to use not just the charge of electrons but also their spin to store and process information. This could lead to faster, more efficient computers. Photons, the particles of light, also have spin. For photons, spin determines something called polarization. Light is an electromagnetic wave, an oscillating electric and magnetic field traveling through space. The direction in which the electric field oscillates is the polarization direction. When we say light is polarized, we mean that the electric fields of all the photons are oscillating in the same direction. Photon spin is related to this. A photon can have spin +1 or spin -1. These correspond to left circular polarization and right circular polarization, two ways that light can twist as it propagates. Polarization is not just an abstract concept, it has practical uses. Polarized sunglasses work by blocking light waves that are polarized in one direction while letting through light polarized perpendicular to that. Light reflected off surfaces like water or roads tends to be horizontally polarized. Polarized sunglasses block this horizontal polarization, reducing glare. Three-dimensional movies use polarization to show different images to each eye. One eye sees light polarized one way, the other eye sees light polarized a different way. Your brain combines the two images, creating the illusion of depth. Many animals can detect polarization. Bees use polarized light patterns in the sky to navigate. Even on cloudy days when the sun is hidden, bees can determine the sun's position by looking at the polarization pattern. Some fish and octopuses can see polarization. They use it to find prey or communicate. It's a whole channel of information that's invisible to us without special instruments. It makes you wonder what other aspects of reality we're missing, because our senses didn't evolve to detect them. Let's think about one more type of particle: quarks. These are the building blocks of protons and neutrons. Protons and neutrons are not fundamental particles, they're made of quarks. A proton consists of 3 quarks, 2 up quarks and 1 down quark. A neutron consists of 1 up quark and 2 down quarks. Quarks, like electrons, have spin. They're fermions with spin 1/2. The spin of quarks contributes to the overall spin of the proton or neutron. The spin structure of protons and neutrons is actually quite complicated and is still an active area of research in particle physics. Understanding how the spins of quarks and the motion of quarks inside a proton combine to give the proton its properties is a challenging problem. But the fundamental principle remains. Everything at the quantum level has spin. It's an intrinsic, unchangeable property. And it affects how particles behave and interact. So from the largest to the smallest, from galaxies to quarks, rotation and spin are everywhere. They're fundamental features of the universe. But let's indulge in a thought experiment. What if all the rotation stopped? What would happen if the cosmic dance came to a halt? This is, of course, completely hypothetical. There's no physical mechanism that could stop all rotation. Conservation of angular momentum is a law of nature. It's built into the structure of space-time itself. But thinking about this impossible scenario helps us appreciate just how important rotation is. Let's start with Earth. Imagine the planet suddenly stopped spinning. The atmosphere and the oceans wouldn't stop immediately. They would keep moving due to their inertia. The atmosphere at the equator is currently moving eastward at over 1,000 miles per hour. If the ground beneath it suddenly stopped, the air would continue forward at that speed. The result would be winds of unimaginable violence, supersonic storms that would scour the surface. Clean, buildings, trees, everything would be obliterated. The oceans would also keep moving, creating tsunamis that would dwarf anything in recorded history. Walls of water hundreds of meters high would wash over the continents. The Earth itself is not a perfect sphere. Because of its rotation, it bulges at the equator. The equatorial diameter is about 43 kilometers larger than the polar diameter. This bulge is maintained by the centrifugal effect of rotation. If rotation stopped, the bulge would collapse. The solid Earth would slowly relax toward a more spherical shape. This would take time because rock is not very fluid, but over years and decades, the crust would adjust. Earthquakes would be common. The redistribution of mass would cause the oceans to flow toward the poles. Sea level at the equator would drop by miles. The polar regions would flood. Without rotation, there would be no day-night cycle. One side of the Earth would face the sun constantly, baking in endless daylight. The other side would be in permanent darkness, freezing cold. The temperature difference between the day side and night side would be extreme. The day side would heat up until the rock itself began to melt. The night side would cool down until even the atmosphere froze and fell as snow. The zone between, the twilight zone, might be somewhat habitable, but conditions would be harsh and constantly changing as the planet slowly wobbled and shifted. Earth's magnetic field, which protects us from solar wind and cosmic radiation, is generated by the motion of liquid iron in the outer core. This motion is driven in part by Earth's rotation. Without rotation, the geodynamo might weaken or shut down. the magnetic field would fade. The solar wind, a stream of charged particles from the sun, would hit the Earth's atmosphere directly. Over time, it would strip away the atmosphere, molecule by molecule. Earth would become more like Mars, which lost its magnetic field billions of years ago and subsequently lost most of its atmosphere. Without an atmosphere, water would evaporate or freeze. Life would be impossible on the surface. Now imagine the entire solar system stopped rotating. The planets would no longer orbit the sun, they would feel only the sun's gravity pulling them inward. Without the sideways motion of their orbits to balance gravity, they would fall toward the sun. The process would be quick in astronomical terms. Earth would spiral inward, reaching the sun in a matter of months. The same would happen to all the planets. Jupiter, despite its great mass, would fall sunward. Saturn, Uranus, Neptune, all would plunge toward their doom. The sun itself, if it stopped rotating, would undergo changes. Its magnetic field, like Earth's, is generated by rotating plasma. Without rotation, the field would weaken. Sunspots and solar flares might cease. The sun's structure might change, though it would still shine as long as fusion continued in the core. But let's think about star formation in a non-rotating universe. Stars form from collapsing gas clouds. Without rotation, a gas cloud that began to collapse under gravity would have nothing to stop it from continuing straight down. It would shrink and shrink, becoming denser and denser. The temperature would rise. But without rotation to create an accretion disk, without centrifugal effects to halt the collapse in some directions, the cloud might collapse all the way down to a black hole without ever igniting as a star. Or if it did ignite, the star might be unstable. Rotation helps stabilize stars. It contributes to the balance between inward gravity and outward pressure. A non-rotating star might behave very differently. It's hard to say if stars would exist at all in a universe without rotation. The night sky might be empty. Galaxies in a non-rotating universe would be unrecognizable. Remember, galaxies are held together by a balance between gravity and motion. Take away the motion and gravity wins. Every star in the galaxy would fall toward the galactic center. The galaxy would collapse from a disk to a dense sphere, or perhaps an even more compact object. Stars would collide, something that almost never happens in our rotating galaxy, because the distances between stars are so vast. In the dense core of a collapsed galaxy, stellar collisions would be common. Stars would merge. Gas would be compressed, triggering intense bursts of star formation, but also feeding the central black hole. The supermassive black hole at the center would grow rapidly as stars and gas fell into it. Eventually, much of the galaxy's mass might end up in the black hole. On the quantum scale, if particles lost their spin, the consequences would be profound and bizarre. Without electron spin, the Pauli exclusion principle wouldn't work the same way. All electrons in an atom could drop into the lowest energy state. Atoms would shrink dramatically. They would become incredibly dense. Chemistry would be completely different. Molecules wouldn't form in the same way. The chemical bonds that hold your body together wouldn't exist. DNA, proteins, lipids, carbohydrates, all the molecules of life would be impossible. You wouldn't exist, neither would anyone else, nor would the Earth, at least not as a solid body. Without the structure provided by atomic orbitals and electron spin, matter would collapse into something much more compact. If photons didn't have spin, light wouldn't have polarization. Electromagnetic waves would propagate differently. Magnetism might not exist in the form we know. The interactions between light and matter, which depend on the properties of photons, would be altered. It's hard to predict all the consequences because so much of physics depends on these quantum properties. But it's safe to say that the universe would be radically different. It probably wouldn't be a universe where life, or at least life as we know it, could exist. So rotation isn't just a curious feature of the cosmos, it's essential. It's woven into the fabric of reality at every scale. From the intrinsic quantum spin of particles, which determines the structure of atoms and the nature of matter, to the rotation of planets, which gives us day and night and seasons, to the spin of galaxies, which holds them together and shapes their structure. Rotation is everywhere. It's unavoidable. It's a consequence of the fundamental laws of physics, particularly the conservation of angular momentum. And it all traces back to those tiny, random fluctuations in the early universe, amplified by inflation, frozen into the structure of space, and carried forward by gravity and angular momentum through 13.8 billion years of cosmic evolution. But let's bring this back to you. Right now, you're lying here, feeling still. Your body is relaxed. Your breathing is slow and steady. You feel anchored, grounded, motionless. And yet, you're part of this grand cosmic motion. You're spinning with the Earth at over 1,000 miles per hour. You're orbiting the sun at 67,000 miles per hour. You're moving with the sun around the galactic center at 500,000 miles per hour. And you're moving with the galaxy through the universe at over 1,000,000 miles per hour. All of this motion is real. It's happening right now, but you don't feel it. You feel perfectly, peacefully still. This is one of the deepest truths about motion and stillness. They're not absolutes, they're relative. There's no such thing as absolute rest, no cosmic reference frame that defines true stillness. You can only measure motion relative to something else. Relative to the Earth beneath you, you're motionless. Relative to the sun, you're racing through space. Relative to distant galaxies, you're moving even faster. Which one is your true state of motion? All of them are, and none of them are. It depends on your perspective, on your frame of reference. This insight that motion is relative was central to Einstein's development of the theory of relativity. There's no preferred viewpoint in the universe, no special location or velocity that's more real than any other. The laws of physics are the same for everyone, regardless of how they're moving. This is called the principle of relativity. It's a profound statement about the symmetry and consistency of nature. And it means that the question, am I really moving or really still, is actually meaningless. The only meaningful question is, am I moving? Relative to something else? And the answer depends on what that something else is. Despite all this motion, despite the dizzying speeds at which we're truly traveling, the universe feels stable. The sun rises and sets with comforting regularity. The seasons change in their annual rhythm. The stars wheel overhead in patterns that have been recognized for thousands of years. This stability is a gift of the conservation laws: conservation of energy, conservation of momentum, conservation of angular momentum. These laws tell us that certain quantities in the universe remain constant. They can change form, be transferred from one object to another, but the total amount never changes. Energy can't be created or destroyed. Momentum can't appear from nowhere. Angular momentum, once established, persists forever unless something transfers it elsewhere. These conservation laws make the universe predictable. They allow us to understand how things work. They let us send spacecraft to other planets and know they'll arrive where we calculated. They let us predict eclipses centuries in advance. They let us build bridges and airplanes and computers, confident that the laws governing their operation won't suddenly change. The universe plays by consistent rules. And those rules include the conservation of angular momentum. This law connects everything that rotates, from electrons to galaxies. It's a thread running through the entire cosmic tapestry, a principle that has been operating since the first moments after the Big Bang and will continue operating until the end of time. Think again about the moon. It's slowly drifting away from Earth, moving farther into space at a few centimeters per year. This has been going on for billions of years. When the moon first formed, about 4.5 billion years ago, it was much closer to Earth, perhaps only 15 to 20,000 kilometers away, compared to about 384,000 kilometers today. Back then, it would have appeared enormous in the sky, perhaps 20 times larger than it does now. The tides it raised on the young Earth were tremendous, perhaps hundreds of meters high. These powerful tides would have dissipated enormous amounts of energy, slowing Earth's rotation much faster than today. Over time, as the moon drifted outward and Earth's rotation slowed down, the tidal forces weakened. The process continues today, but at a much gentler pace. The moon's recession is not unique. It's a general consequence of tidal interactions. Many moons in the solar system are slowly moving away from or toward their planets, depending on the details of their orbits and rotation rates. Mars's moon Phobos, for example, is actually moving closer to Mars. It orbits faster than Mars rotates, so the tidal bulge it raises on Mars pulls it backwards, slowing its orbit. When an orbit slows, it shrinks. Phobos will eventually crash into Mars or be torn apart by tidal forces, forming a ring system. This will happen in about 50 million years, a blink of an eye in geological time. Saturn's moon, Enceladus, is another fascinating case. It's a small, icy world, only about 500 kilometers across, but it's geologically active. It has geysers that spray water ice into space from cracks at its south pole. The source of energy for this activity is tidal heating. Enceladus is locked in an orbital resonance with another moon, Dione. This resonance causes Enceladus's orbit to be slightly elliptical rather than circular. As Enceladus orbits Saturn, the tidal forces it feels vary. Sometimes it's stretched more, sometimes less. This flexing generates heat through friction, melting ice beneath the surface and powering the geysers. It's a direct example of how orbital dynamics and tidal interactions can create geological activity. And it's all driven by angular momentum and gravity. Jupiter's moon Io is the most volcanically active body in the solar system. It has hundreds of active volcanoes. The surface is constantly being resurfaced by lava flows. The source of all this volcanic energy is tidal heating from Jupiter. Io is locked in a resonance with two other large moons, Europa and Ganymede. This resonance forces Io's orbit to be eccentric. As Io orbits Jupiter, the tidal forces vary, stretching and squeezing the moon. This generates tremendous heat. The interior of Io is partially molten. The volcanoes erupt continuously. The moon's surface is covered in sulfur and sulfur dioxide, giving it a yellow, orange, and red appearance. It looks like a giant pizza. And in fact, when Voyager first sent back images of Io, one scientist remarked that it looked better than any pizza he'd ever seen. These examples show that rotation and orbital dynamics are not abstract concepts. They have real, observable consequences. They shape the worlds of our solar system. They determine which moons are active and which are dead. They control where we find liquid water, a key ingredient for life. Europa, another moon of Jupiter, is thought to have a global ocean of liquid water beneath its icy crust. This ocean is kept liquid by tidal heating, the same process that melts Io's interior. Europa is one of the best places in the solar system to search for life beyond Earth. And the reason it might be habitable is ultimately due to the interplay of orbits, resonances, and tidal forces, all governed by angular momentum and gravity. Let's return to the Milky Way for a moment. Our galaxy is not alone in the universe. It's part of a group of galaxies called the Local Group. This group includes about 50 galaxies, most of them small dwarf galaxies. The largest members are the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy. These galaxies are bound together by gravity. They orbit their common center of mass, a point somewhere between the Milky Way and Andromeda, since those two are the most massive. Andromeda, also known as M31, is about 2.5 million light-years away from us. It's the nearest large galaxy. On a dark night, away from city lights, you can see it with the naked eye as a faint, fuzzy patch. It's actually one of the most distant objects you can see without a telescope. When you look at Andromeda, you're seeing light that left that galaxy 2.5 million years ago. You're looking back in time. In that sense, astronomy is a form of time travel. We can never see the universe as it is now, only as it was in the past. Andromeda and the Milky Way are on a collision course. They're moving toward each other at about 110 kilometers per second. In about 4 billion years, the two galaxies will begin to merge. This sounds catastrophic, and in a sense it is, but it's also a slow, majestic process. The galaxies will pass through each other, their stars rarely colliding because the distances between stars are so vast. But the gravitational interactions will be intense. Stars will be flung into new orbits. The shapes of the galaxies will distort. Gas clouds will collide, compressing and triggering massive bursts of star formation. The night sky, viewed from Earth, will be spectacular. Andromeda will loom larger and larger, eventually filling much of the sky. The two galaxies will merge and separate over hundreds of millions of years, until finally they settle into a single, larger galaxy. This merged galaxy will be an elliptical, a more rounded shape without the distinct spiral arms of the current galaxies. The merger will disrupt the organized rotation of both spirals. The end result will still rotate, but not in the orderly disc-like fashion. Some have nicknamed the future merged galaxy Milkomeda, a portmanteau of Milky Way and Andromeda. Our sun, if it still exists at that point, will be flung into a new orbit, possibly farther from the galactic center or closer to it. Earth, if it survived the sun becoming a red giant, would go along for the ride. Life on Earth, if it still existed, would witness an unimaginably beautiful sky, full of bright new stars born from the collision-triggered star formation. Galaxy mergers are common in the universe. We see them happening at various stages all around us, at various distances. Some are just beginning, two spirals approaching each other. Some are in the midst of merging, their shapes distorted and tangled. Some have completed the process, forming elliptical galaxies. These mergers are driven by gravity, and they redistribute angular momentum. When two galaxies collide, their angular momentum vectors might not be aligned. They might be rotating in different directions. The merger process has to somehow combine these different angular momenta. The result is complex. Some material ends up in the merged galaxy. Some is flung out into space, forming tidal tails, long streams of stars and gas extending away from the merger site. These tails can stretch for hundreds of thousands of light years. They're beautiful and dramatic evidence of the merger process. Now let's talk about something truly exotic. Pulsars. These are rapidly spinning neutron stars, and they're among the most extreme objects in the universe. Neutron stars form when massive stars explode as supernovas. The core of the star collapses in a fraction of a second. The electrons and protons are squeezed together so hard that they combine to form neutrons. The result is a ball of neutrons about 20 kilometers across, with a mass greater than the sun. A neutron star is the densest form of matter we know of, aside from black holes. A teaspoon of neutron star material would weigh about 1 billion tons. And neutron stars spin fast, very fast. When the core of the star collapses, it conserves its angular momentum. The original star was rotating slowly, perhaps once every few days or weeks. But when the core collapses from a diameter of thousands of kilometers down to only 20 kilometers, its rotation speed increases dramatically. It's the ice skater pulling in their arms, taken to the extreme. Some neutron stars rotate hundreds of times per second. The fastest known pulsar, named PSR J17482446 AD, spins 716 times per second. That's faster than a kitchen blender. At the surface of this neutron star, material is moving at about 1/4 of the speed of light. The centrifugal effects are enormous, nearly enough to tear the star apart. But gravity holds it together just barely. Neutron stars have incredibly strong magnetic fields, typically 1 trillion times stronger than Earth's field. Some, called magnetars, have fields even stronger, up to 1 quadrillion times Earth's field. These magnetic fields are generated by the motion of charged particles in the star's interior, and by the extreme compression of the stellar material during collapse. The magnetic axis of a neutron star is usually not aligned with its rotation axis. As the star rotates, the magnetic field sweeps through space. Charged particles in the magnetic field are accelerated to high energies. They emit radiation, typically radio waves, but sometimes X-rays or gamma rays. This radiation is beamed along the magnetic axis, so as the star rotates, the beam sweeps around like a lighthouse beam. If Earth happens to lie in the path of the beam, we see a pulse of radiation every time the beam sweeps past us. That's why we call them pulsars. They pulse. The pulses are incredibly regular, like the ticking of a cosmic clock. In fact, some pulsars keep time as accurately as the best atomic clocks on Earth. The rotation of a neutron star is extraordinarily stable. It's governed by the star's moment of inertia and its angular momentum, and these don't change much over time. This regularity makes pulsars useful for a variety of scientific purposes. Astronomers use pulsars to test the laws of physics under extreme conditions. General relativity makes specific predictions about how objects behave in strong gravitational fields. Neutron stars are perfect laboratories for testing these predictions. One famous example is the Hulse-Taylor binary, a system of 2 neutron stars orbiting each other every 8 hours. One of the stars is a pulsar, so we can time its pulses with great precision. By measuring how the arrival time of the pulses changes, astronomers can track the orbit of the system with incredible accuracy. According to general relativity, 2 massive objects orbiting each other should emit gravitational waves, ripples in space-time that carry energy away from the system. This should cause the orbit to gradually shrink. the two stars should spiral closer together. Russell Hulse and Joseph Taylor discovered this binary system in 1974 and monitored it for many years. They found that the orbit was indeed shrinking at exactly the rate predicted by general relativity. This was the first indirect evidence that gravitational waves exist. It confirmed a major prediction of Einstein's theory. For this discovery, Hulse and Taylor were awarded the Nobel Prize in Physics in 1993. Since then, we've directly detected gravitational waves using ground-based instruments called LIGO and Virgo. These detectors have observed gravitational waves from merging black holes and merging neutron stars, opening up an entirely new way to observe the universe. Pulsars are also used as cosmic GPS. By carefully timing the pulses from many pulsars spread across the sky, astronomers can detect tiny variations caused by gravitational waves passing through our region of space. This technique is called pulsar timing arrays. It's sensitive to very low-frequency gravitational waves, lower than ground-based detectors can sense. These low-frequency waves might be produced by supermassive black holes merging in distant galaxies. Pulsar timing arrays are currently searching for these signals. They may already be seeing hints of them. It's an exciting frontier in astronomy. Now let's think about the Coriolis effect again, but in more depth. We mentioned it earlier in the context of weather and ocean currents. The Coriolis effect is a consequence of the Earth's rotation. It causes moving objects on Earth's surface to be deflected. In the northern hemisphere, they're deflected to the right. In the southern hemisphere, to the left. This deflection affects anything that moves across significant distances, including air, water, aircraft, and long-range projectiles. The Coriolis effect arises because different parts of the Earth's surface are moving at different speeds. At the equator, the surface is moving eastward at about 1,670 kilometers per hour. At 30 degrees latitude, the speed is about 1,440 kilometers per hour. At 60 degrees latitude, it's about 830 kilometers per hour. At the poles, the surface isn't moving at all, except for the rotation itself. Now imagine air moving from the equator toward the North Pole. It starts with the eastward velocity of the equator. As it moves north, it passes over ground that's moving more slowly eastward. Relative to that ground, the air is moving faster eastward. It appears to curve to the right. This deflection drives the large-scale wind patterns on Earth. Near the equator, warm air rises. It moves toward the poles at high altitude. As it moves, it's deflected by the Coriolis effect. By the time it reaches about 30 degrees latitude, it has curved so much that it's moving almost due east. At that point, it sinks back toward the surface. This creates a circulation pattern called the Hadley cell. The sinking air at 30 degrees creates high-pressure zones, which tend to be dry. This is why many of the world's deserts, including the Sahara, are located around 30 degrees latitude. The air that sinks then flows back toward the equator at the surface, but it's also deflected by the Coriolis effect. This creates the trade winds, which blow from the northeast in the northern hemisphere and from the southeast in the southern hemisphere. Similar circulation cells exist at higher latitudes. The Ferrel cell operates between about 30 and 60 degrees. The polar cell operates between about 60 degrees and the poles. These cells, driven by solar heating and shaped by the Coriolis effect, create the prevailing wind patterns we observe. The westerlies at mid-latitudes, the polar easterlies near the poles. All of this is a consequence of Earth's rotation and the fact that different latitudes are moving at different speeds. Ocean currents are also affected by the Coriolis effect. The major ocean gyres, the large circular current systems in each ocean basin, rotate clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. This is due to the Coriolis deflection. The gyres redistribute heat around the planet. The Gulf Stream, for example, carries warm water from the Gulf of Mexico across the North Atlantic toward Europe. This keeps Europe much warmer than it would otherwise be at its latitude. Without the Gulf Stream, Europe's climate would be more like Canada's. The formation and behavior of ocean currents are intimately connected to Earth's rotation. Even aviation is affected by the Coriolis effect. When planning long-distance flights, pilots must account for it. If you're flying from the equator to a high latitude, you can't just aim straight at your destination. By the time you get there, the Earth will have rotated beneath you and you'll miss your target. You have to adjust your heading to compensate. Similarly, long-range artillery must account for the Coriolis effect. During World War I, big naval guns were firing shells over distances of tens of kilometers. At those ranges, the Coriolis deflection was significant. If gunners didn't account for it, their shells would miss by hundreds of meters. There's a famous myth about the Coriolis effect and toilets. The myth says that toilets in the northern hemisphere flush counterclockwise, while toilets in the southern hemisphere flush clockwise. This is not true. The Coriolis effect at the scale of a toilet is far too weak to influence the direction of water draining. The direction is determined by the shape of the bowl and the initial motion of the water. You can make a toilet flush in either direction in either hemisphere just by giving the water a little initial swirl. But the myth persists, repeated in travel guides and television shows. It's a good example of how scientific concepts can be misunderstood and misapplied. Let's think about one more consequence of rotation: the equatorial bulge and its effects on satellites. We mentioned that Earth bulges at the equator due to its rotation. This bulge is significant, about 21 kilometers. It means that the gravitational field of Earth is not perfectly symmetrical. The field is slightly stronger at the poles and slightly weaker at the equator. This asymmetry affects satellites orbiting Earth. A satellite's orbit is determined by the gravitational field it experiences. If the field were perfectly symmetrical, the satellite would orbit in a fixed plane. But because of the equatorial bulge, the orbit precesses. The orbital plane slowly rotates around Earth's axis. This precession can be a nuisance for some satellites, but it's useful for others. Sun-synchronous orbits take advantage of precession to keep the satellite's orbital plane aligned with the Sun. The satellite passes over the same parts of Earth at the same local solar time every day. This is useful for Earth observation satellites, which can then compare images taken at the same time of day, ensuring consistent lighting conditions. The precession rate depends on the satellite's altitude and inclination. By choosing the right orbit, you can make the precession exactly match the rate at which Earth orbits the Sun, keeping the orbital plane fixed relative to the Sun. The Moon also causes perturbations to satellite orbits through its gravity, and the Sun does too. Predicting the exact motion of a satellite requires accounting for all these effects. The Earth's gravity field is not a simple sphere. It has bumps and lumps corresponding to mountains, ocean trenches, and variations in crustal density. Satellites feel all these variations. Mapping Earth's gravity field with high precision has been the goal of several satellite missions, including GRACE, the Gravity Recovery and Climate Experiment. By measuring tiny changes in the distance between two satellites orbiting in formation, GRACE created detailed maps of Earth's gravity field. These maps reveal information about mass distribution underground, ocean currents, ice sheets, and even groundwater depletion. Now let's think about rotation in the context of relativity and time. Einstein's theory of relativity tells us that time is not absolute. It can pass at different rates for different observers, depending on their motion and the gravitational field they're in. One of the predictions of relativity is that clocks moving relative to each other tick at different rates. A clock in motion ticks more slowly than a stationary clock. This is called time dilation. It's been confirmed by many experiments. Atomic clocks flown on airplanes run at different rates than identical clocks left on the ground. The difference is tiny, only billionths of a second, but it's measurable and it matches the predictions of relativity. But relativity also predicts that rotation affects time. Imagine two clocks, one at the center of a rotating disk and one at the edge. The clock at the edge is moving faster through space than the clock at the center. According to relativity, it should tick more slowly. This effect is real. It's been measured using atomic clocks on Earth. A clock at the equator, which is moving faster due to Earth's rotation, ticks slightly more slowly than a clock at the North Pole. The difference is incredibly small, only about 100 nanoseconds per day, but it's detectable with precise atomic clocks. This effect has to be accounted for in the Global Positioning System, GPS. GPS satellites carry atomic clocks that broadcast time signals. Your GPS receiver uses signals from multiple satellites to determine your position. The calculations depend on knowing the exact time from each satellite. But the satellites are moving relative to the ground, and they're at high altitude where Earth's gravitational field is weaker. Both of these effects cause time dilation. The satellites' clocks tick at a different rate than clocks on the ground. If this wasn't accounted for, GPS positions would be wrong by several kilometers after just one day. Engineers program the satellite's clocks to tick at a slightly different rate to compensate for relativistic effects. GPS is a practical, everyday technology that relies on Einstein's theory of relativity to work correctly. Every time you use a navigation app on your phone, you're using relativity. Rotation also plays a role in the twin paradox, a famous thought experiment in relativity. Imagine two twins. One stays on Earth. The other travels to a distant star and back at high speed. According to relativity, the traveling twin will age less than the stay-at-home twin. Time passes more slowly for the moving twin. This seems paradoxical because, from the traveling twin's perspective, it's the Earth that's moving away and coming back. Shouldn't the Earth twin be the one who ages less? The resolution of the paradox is that the situation is not symmetrical. The traveling twin has to accelerate to turn around and come back. Acceleration breaks the symmetry. The traveling twin really does age less. This has been confirmed by experiments with particles and with atomic clocks. Rotation is a form of acceleration. If you're on a rotating platform, you're constantly changing direction, and that means you're accelerating. This acceleration can lead to time dilation effects similar to those in the twin paradox. If one twin stays at the center of a rotating disk and the other twin rides at the edge twin will age more slowly. This is sometimes called the rotating disk paradox or the Ehrenfest paradox, and it's been the subject of much analysis in relativity theory. The connection between rotation and time brings us full circle to the beginning of our journey. We started by thinking about why everything spins. Now we see that rotation affects time itself. The fabric of reality is woven from space, time, and motion. They're all interconnected. You can't fully understand one without understanding the others. The universe is a dynamic, evolving system where everything influences everything else. Rotation is a thread that runs through the entire cosmos, from the quantum realm to the largest structures we can observe. As you lie here approaching sleep, you're a part of all this. The atoms in your body have quantum spin. Your body is rotating with the Earth is orbiting the Sun is orbiting the galaxy is moving through the universe. All of it is connected by gravity, by angular momentum, by the laws of physics that have governed the cosmos since the Big Bang. You're not separate from the universe. You're an integral part of it. Every breath you take, every thought you have, every dream you dream is a manifestation of the universe experiencing itself. The conservation of angular momentum ensures that the cosmic dance will continue. Stars will form and die. Planets will orbit and evolve. Galaxies will spin and merge. And through it all, the fundamental laws will remain constant. The universe plays by rules, and those rules, while sometimes strange and counterintuitive, are beautiful and elegant. They connect the smallest to the largest, the simplest to the most complex. They give structure to chaos. They turn randomness into pattern. They create a cosmos where matter can organize itself into stars, planets, and eventually, life. You are the universe's way of knowing itself. Your consciousness, your ability to think and wonder and understand, is perhaps the most remarkable thing the universe has produced. From the quantum fluctuations in the early universe to the stars forging heavy elements to the evolution of life on Earth, every step of the journey has led to this moment, to you lying here contemplating the cosmos. The universe spent 13.8 billion years preparing for this moment. It's all been building to you, to the consciousness that can look back through time and space and see the story. That can understand the laws, that can appreciate the beauty of it all. And at the heart of that beauty is motion, the endless cosmic dance. From the spin of an electron to the rotation of a galaxy, everything moves, everything turns. And in that motion is stability. In that spin is structure. The paradox of stillness and motion resolves itself. You are still relative to your immediate surroundings. You are moving relative to the cosmos. Both are true, both are real, and both are essential to who and what you are. So rest easy. Let the gentle rhythm of your breath carry you into sleep. Know that you're held by the same laws that hold the stars and galaxies. You're spinning through space at incredible speeds, and yet you're perfectly safe, perfectly still, perfectly at peace. The ancient civilizations looked up at the spinning stars and saw patterns. They saw stories. The Greeks saw heroes and monsters frozen in the sky. The Egyptians saw their gods. The Maya tracked the movements of Venus with incredible precision, using it to time their agricultural cycles and religious ceremonies. They didn't know they were watching the result of angular momentum conservation. They didn't know about gravity or orbital mechanics. But they recognized patterns. They saw order in the heavens. And that order is real. It's a consequence of the physical laws we've been exploring. The zodiac constellations, familiar to anyone who reads horoscopes, mark the path of the sun across the sky over the course of a year. This path is called the ecliptic. It's the plane of Earth's orbit around the sun projected onto the celestial sphere. The planets also move along the ecliptic because all the planets orbit in roughly the same plane. This is not a coincidence. It's a consequence of how the solar system formed from a rotating disk. The disk was flat, so the orbits are all roughly in the same plane. When you see Mars or Jupiter in the night sky, they're always near the ecliptic, near the zodiac constellations. Ancient astronomers noticed this. They called the planets wanderers because unlike the fixed stars, the planets moved against the background of constellations. This motion is the orbital dance, the circulation of the planets around the sun, all moving in the same direction, all consequences of that original rotating disk from which the solar system formed. The precession of the equinoxes is another subtle effect of rotation. Earth's axis wobbles slowly over time like a spinning top that's starting to slow down. This wobble is caused by the gravitational pull of the sun and moon on Earth's equatorial bulge. The pull creates a torque, a twisting force, that tries to align Earth's axis perpendicular to its orbital plane. But Earth is spinning, and when you apply a torque to a spinning object, it doesn't tip over. Instead, it precesses. Its axis traces out a circle in space. For Earth, this precession takes about 26,000 years to complete one cycle. The precession means that the direction Earth's axis points changes over time. Right now, the North Pole points toward Polaris, the North Star. But 5,000 years ago, it pointed toward a different star, Thuban. In another 12,000 years, it will point toward Vega. The precession also means that the position of the sun against the background stars at the equinoxes changes over time. This is why astrology's zodiac signs are off from the actual constellations now. The zodiac was defined thousands of years ago, but precession has shifted things. If you're born under the sign of Aries, the sun was actually in the constellation Pisces when you were born. Astrology doesn't account for precession. Precession affects the seasons too, though very slowly. Currently, Earth is closest to the sun during northern hemisphere winter. This makes northern winters slightly milder and southern summers slightly cooler than they would otherwise be. But precession will gradually shift this. In about 11,000 years, Earth will be closest to the sun during northern summer. This will make northern summers hotter and winters colder, amplifying seasonal extremes. These changes happen so slowly that they're not noticeable within a human lifetime, but over tens of thousands of years, they have significant effects on climate. They're part of the Milankovitch cycles, variations in Earth's orbit and axial tilt, that affect how much solar radiation different parts of Earth receive at different times. These cycles are thought to play a role in triggering ice ages and interglacial periods. Let's think about Jupiter's role in the solar system. Jupiter is massive, more than twice the mass of all other planets combined. Its gravity has a profound influence on the rest of the solar system. Jupiter acts as a cosmic shepherd, its gravity affecting the orbits of asteroids and comets. The asteroid belt, located between Mars and Jupiter, is shaped by Jupiter's gravity. There are gaps in the belt called Kirkwood gaps, where almost no asteroids are found. These gaps occur at distances where an asteroid's orbital period would be a simple fraction of Jupiter's period, like 1/2 or 1/3. At these locations, the asteroid receives regular gravitational tugs from Jupiter at the same point in its orbit. Over time, these tugs add up, and the asteroid is either flung out of that orbit or pushed into a different one. The gaps are cleared out. Jupiter also protects the inner solar system from comets. Comets are icy bodies from the outer reaches of the solar system. Sometimes their orbits are perturbed and they fall inward toward the sun. Many of these comets encounter Jupiter. Jupiter's strong gravity can capture them, throw them into different orbits, or even eject them from the solar system entirely. Without Jupiter, Earth would be hit by comets much more frequently. Some of these impacts could be devastating, causing mass extinctions. Jupiter acts as a shield, taking hits that might otherwise strike Earth. This may have been important for the development of life on our planet. Life needs stability. Frequent massive impacts would make it hard for complex ecosystems to develop. Jupiter provides some of that stability. Saturn, the second largest planet, is famous for its rings. These rings are made of countless particles of ice and rock, ranging in size from tiny grains to house-sized boulders. The rings extend hundreds of thousands of kilometers from Saturn, but are only about 10 meters thick in most places. They're incredibly flat, a consequence of collisions between particles and the conservation of angular momentum. Any particle with an orbit tilted out of the main plane will eventually collide with other particles. These collisions tend to bring all the particles into the same plane. Over time, the rings flatten. The rings are also divided into distinct bands separated by gaps. Some of these gaps are caused by small moons embedded in the rings. These shepherd moons gravitationally clear out the material around them. The most famous gap, the Cassini division, is about 4,700 kilometers wide. It's caused by a resonance with Saturn's moon Mimas. Particles in the Cassini division orbit Saturn twice for every one orbit of Mimas. This resonance causes their orbits to become unstable, and they're gradually cleared out. Saturn's rings are probably not permanent features. They're thought to be relatively young, perhaps only a few 100 million years old. They may have formed from the destruction of a small moon or a comet that wandered too close to Saturn and was torn apart by tidal forces. Over time, the rings are slowly spiraling inward, raining down on Saturn. In a few 100 million years, they may be gone. Future civilizations, if there are any, might look at Saturn and see a planet without rings, not realizing what they missed. Uranus and Neptune, the ice giants, are less well studied than the gas giants because they're so far away. Only one spacecraft, Voyager 2, has visited them, briefly flying past each planet. But those brief encounters revealed fascinating worlds. Uranus, with its extreme axial tilt, has the strangest seasons in the solar system. For part of its 84-year orbit, one pole faces the sun continuously, experiencing 42 years of daylight, while the other pole experiences 42 years of darkness. Then the roles reverse. The dynamics of Uranus's atmosphere under these conditions are complex and still not fully understood. Neptune has the strongest winds in the solar system, with speeds exceeding 2,000 kilometers per hour. This is surprising because Neptune is so far from the sun and receives very little solar energy. The winds must be powered by internal heat, energy left over from the planet's formation, and ongoing gravitational contraction. Neptune also has a large moon, Triton, which orbits in the opposite direction to Neptune's rotation. This retrograde orbit suggests that Triton didn't form with Neptune but was captured. Capture is difficult and requires the right circumstances. Triton probably once orbited the Sun as a dwarf planet, similar to Pluto. It wandered too close to Neptune and was captured, possibly during an interaction, that ejected another moon. Triton's orbit is slowly decaying. In a few billion years, it will get too close to Neptune and be torn apart by tidal forces, possibly forming a spectacular ring system. Beyond Neptune lies the Kuiper Belt, a region filled with icy bodies left over from the solar system's formation. Pluto is the most famous resident of the Kuiper Belt, though it's by no means the largest. Eris, another dwarf planet, is slightly more massive. There are thousands of known Kuiper Belt objects, and probably millions more too small to detect from Earth. These objects are pristine samples of the material from which the outer solar system formed. Studying them tells us about conditions in the early solar system. Several spacecraft have visited or are on their way to visit Kuiper Belt objects. New Horizons flew past Pluto in 2015, returning stunning images of a complex, geologically active world. It then continued on to visit another Kuiper Belt object, Arrokoth, in 2019. These missions are expanding our understanding of the distant reaches of our solar system. Even farther out, beyond the Kuiper Belt, lies the hypothetical Oort cloud, a vast spherical shell of comets surrounding the solar system. The Oort cloud has never been directly observed, but its existence is inferred from the orbits of long-period comets that take hundreds or thousands of years to orbit the Sun. These comets come from all directions, not just from the plane of the solar system. This suggests they originate from a spherical distribution of objects surrounding the Sun. The Oort cloud may extend halfway to the nearest star, marking the outermost boundary of the Sun's gravitational influence. Comets from the Oort cloud are occasionally perturbed by the gravity of passing stars or by the tidal force of the Milky Way's galactic disk. These perturbations can send comets falling inward toward the Sun. As a comet approaches the inner solar system, solar radiation heats it. Ice sublimates, turning directly from solid to gas. This gas carries dust with it, forming a glowing coma around the comet's nucleus and often producing spectacular tails. Comets have two tails, a dust tail and an ion tail. The dust tail is pushed by the pressure of sunlight and curves along the comet's orbit. The ion tail is pushed by the solar wind and always points directly away from the Sun. Both tails can stretch millions of kilometers through space. Historically, comets were seen as omens, signs of disaster, or great change. This is understandable. They appeared suddenly, often became very bright, and then slowly faded away over weeks or months. They didn't follow the predictable patterns of the planets and stars. We now know that comets are simply icy leftovers from the solar system's formation, following orbits that occasionally bring them close to the Sun. They're not omens, they're time capsules, preserving material from the early solar system in their frozen hearts. Some comets have very short orbital periods, returning regularly. Halley's Comet is the most famous, returning every 76 years. Its last appearance was in 1986, and it will return in 2061. Halley's Comet has been recorded by astronomers for over 2,000 years. It appeared in 76 BC, and there are Chinese records of it. It was in the sky in 1066 AD during the Norman conquest of England, and it's depicted in the Bayeux Tapestry. Edmund Halley, in the 17th century, realized that comet sightings from 1531, 1607, and 1682 were actually the same comet returning. He predicted it would return in 1758. He didn't live to see it, but when the comet appeared on schedule, it was named in his honor. Short-period comets like Halley have had their orbits changed by gravitational interactions with planets, particularly Jupiter. They've been captured into shorter orbits. They lose material every time they pass near the Sun, so they have finite lifetimes. Eventually, they'll either disintegrate entirely, break up, or become dormant with all their ice gone, leaving behind an inert, rocky core. Some asteroids may actually be dead comets that have lost all their volatile material. Meteor showers are another consequence of comets. As a comet orbits the Sun, it leaves behind a trail of dust and small particles along its orbit. When Earth's orbit intersects this trail, the particles enter Earth's atmosphere at high speed and burn up, creating streaks of light we call meteors or shooting stars. Many meteor showers are associated with known comets. The Perseids, visible every August, are debris from Comet Swift-Tuttle. The Leonids in November come from Comet Tempel-Tuttle. The Geminids in December are associated with an object called Phaethon, which may be an asteroid or a dead comet. These showers happen at the same time every year because Earth passes through the debris trail at the same point in its orbit. The number of meteors you see depends on how much debris is in the trail and how directly Earth passes through it. Occasionally, larger objects enter Earth's atmosphere. Most burn up completely, but some survive to reach the ground as meteorites. Thousands of meteorites have been found and studied. They're pieces of asteroids, sometimes pieces of the Moon or Mars knocked off by impacts. Meteorites provide direct samples of material from other worlds. We've learned a lot about the composition and history of the solar system by studying meteorites. Some meteorites are very old, dating back to the formation of the solar system 4.5 billion years ago. They contain tiny grains that formed before the solar system in the atmospheres of earlier generations of stars. These pre-solar grains are the oldest solid material we can hold in our hands. Large impacts, while rare, have had profound effects on Earth's history. About 66 million years ago, an asteroid or comet about 10 kilometers across struck Earth near what is now the Yucatan Peninsula in Mexico. The impact released energy equivalent to billions of nuclear bombs. It created a crater almost 200 kilometers across. Tsunamis swept across the oceans. Dust and debris were thrown into the atmosphere. blocking sunlight for months or years. The global climate cooled. Plants couldn't photosynthesize. Food chains collapsed. About 75% of all species went extinct, including the non-avian dinosaurs. This event, the Cretaceous-Paleogene extinction, changed the course of life on Earth. Mammals, which had been small and relatively unimportant, diversified and eventually gave rise to us. The impact that killed the dinosaurs was not the only mass extinction in Earth's history. There have been 5 major mass extinctions, and the causes of most of them are still debated. Volcanic eruptions, climate change, ocean chemistry changes, and impacts have all been implicated. But the end Cretaceous extinction is the best understood, largely because the evidence is so clear. There's a thin layer of rock all around the world, dating to 66 million years ago, that's enriched in iridium, an element rare on Earth but common in asteroids. This iridium layer is the smoking gun, the fingerprint of the impact. Below the layer, you find dinosaur fossils. Above it, you don't. Impacts continue today, though most are small. Every day, Earth gains about 44 tons of mass from space dust and small meteorites. Most of this burns up in the atmosphere. Larger impacts are rare. An object a few meters across might hit once a year, creating a fireball in the sky. An object a few tens of meters across might hit once a century. The Tunguska event in 1908 was probably caused by an object about 50 meters across that exploded in the atmosphere over Siberia. It flattened trees over an area of 2,000 square kilometers. Fortunately, the area was remote and unpopulated. A similar impact over a city would be catastrophic. An object large enough to cause a global catastrophe, like the one that killed the dinosaurs, might hit Earth only once every 100 million years or so. That sounds like a long time, but it's not infinite. The risk exists. This is why astronomers are searching for near-Earth asteroids. We want to find them all, or at least all the large ones. If we find one on a collision course with Earth and we find it far enough in advance, we might be able to deflect it. A small push applied years before the predicted impact could be enough to make the asteroid miss Earth. This isn't science fiction, it's a realistic application of our understanding of orbital mechanics and gravity. In 2022, NASA's DART mission deliberately crashed a spacecraft into a small asteroid to test this technique. The impact successfully changed the asteroid's orbit. It was a proof of concept, showing that we have the technology to defend Earth if we need to. Now let's think about life and rotation. Life on Earth evolved in the context of the planet's rotation. The day-night cycle is one of the most fundamental rhythms of the biosphere. Almost all organisms have internal biological clocks, circadian rhythms that match the 24-hour day. These clocks regulate sleep, metabolism, hormone production, and countless other processes. Even organisms that live in environments without light, like deep caves or the deep ocean, maintain circadian rhythms. The rhythm is internal, encoded in genes and biochemical feedback loops. But these internal clocks need to be synchronized to the external world, otherwise they drift. In humans, the primary cue for synchronization is light. Specialized cells in the retina detect light and send signals to a region of the brain called the suprachiasmatic nucleus, the master clock. This clock then coordinates rhythms throughout the body. Without light cues, as in experiments where people live in constant darkness, the circadian rhythm tends to drift to a period slightly longer than 24 hours, usually about 24.5 hours. This suggests that our internal clock is set by evolution to be just slightly slow, so that light exposure each morning resets it, keeping it synchronized. Disruption of circadian rhythms has health consequences. Shift workers who work at night and sleep during the day have higher rates of various health problems, including obesity, diabetes, and cardiovascular disease. This is thought to be because their internal clocks are constantly out of sync with their schedules. Jet lag is another consequence of circadian disruption. When you travel across time zones, your internal clock doesn't immediately adjust. You feel tired at the wrong times. It takes several days for your clock to resynchronize to the new local time. The direction of travel matters. Most people find it easier to adjust to westward travel, which lengthens the day, than eastward travel, which shortens it. This is consistent with the natural tendency of the internal clock to run slightly slow. Seasonal rhythms are another consequence of Earth's rotation and axial tilt. Many organisms respond to the changing length of days across the year. This response, called photoperiodism, allows organisms to anticipate seasonal changes and adjust their behavior accordingly. Birds use day length to time their migrations and breeding. Many mammals breed at specific times of year so that their young are born when food is abundant. Plants use day length to time flowering. Short day plants flower when nights become longer than a critical length. Long day plants flower when nights become shorter. This mechanism ensures that flowering happens at the right time of year for pollination and seed production. The timing of seasonal events has been shifting in recent decades due to climate change. Spring is arriving earlier, plants are flowering earlier, birds are migrating earlier. These shifts can cause mismatches. If a bird migrates based on day length, but its food source appears based on temperature, and the temperature is warming faster than the day length is changing, the bird might arrive too late to take advantage of peak food availability. These phenological mismatches are a concern for conservation biologists. They're one of the many ways that rapid climate change can disrupt ecosystems. The rotation of the Earth also creates wind and ocean current patterns that redistribute heat around the planet, making much of Earth habitable. Without the rotation-driven Coriolis effect shaping these patterns, climate would be very different. The tropics might be even hotter, the poles even colder. The temperate zones, where most human civilization has developed, might not exist in the same form. And it's a story that connects us directly to the cosmos, showing how the universe created the galaxies, how the galaxies created the stars, how the stars created the elements, and how the elements eventually assembled into planets and life. As you drift deeper into sleep now, let your mind wander among the galaxies. Imagine yourself floating in intergalactic space, looking out at the cosmic web, seeing the filaments and nodes, the voids and clusters. Picture the galaxies as they were billions of years ago, smaller and more numerous, constantly colliding and merging. Watch as they grow over cosmic time, building up mass, forming stars, creating the familiar shapes we see today. See the spiral galaxies rotating gracefully, their arms glowing with young blue stars, new solar systems forming in molecular clouds. See the elliptical galaxies, smooth and red, filled with ancient stars, the products of long-ago mergers. See the dwarf galaxies, small but numerous, the building blocks that larger galaxies continue to accrete. See the galaxy clusters, great cities of galaxies bound together by gravity, containing thousands of individual systems. And at the center of each large galaxy, picture the supermassive black hole, invisible but powerful, feeding on gas, generating feedback, regulating the growth of its host. Picture the jets launching from actively feeding black holes, shooting out perpendicular to the accretion disk, carrying energy far into intergalactic space. Picture the winds driven by radiation pressure, pushing gas out of the galaxy, glowing in X-rays as they plow through the surrounding medium. Zoom in closer to one galaxy, our own Milky Way. See the spiral arms, the central bulge, the disk, the halo. See the sun, just one of hundreds of billions of stars, located about halfway out from the center, orbiting through one of the spiral arms. See the solar system, the planets in their orbital planes, Earth a small blue dot, third from the sun. And on that blue dot, in one particular place, there's you. Connected to all of this, made of atoms forged in ancient stars, living in a galaxy that formed through the merger of countless protogalaxies over billions of years. Part of a cosmic story that began with the Big Bang and continues today, a story of structure formation, of complexity emerging from simplicity, of light emerging from darkness. You are part of the universe. The universe is part of you. And the story of galaxy formation is the story of how that connection came to be, how the raw materials created in the Big Bang were shaped by gravity and time into the magnificent structures we see when we look up at the night sky. Rest now, let the cosmos carry you into sleep, and know that when you dream, you're dreaming with stardust, with atoms that have journeyed through space and time, through galaxies and stars, to arrive at this moment. Thank you for joining me on this cosmic drift through the story of how galaxies are born. If you enjoyed this journey, I'd love to hear about your favorite moment or insight in the comments below. And if you'd like to drift through more cosmic mysteries with me, consider subscribing to the channel. Until next time, sleep well and let your dreams take you among the stars. Good night.